hit that bell. So it is explanation time. Water, salt, ice, and energy exchange. This is such a cool experiment to do at home. You really should try it. You just need big jar, usually glass or metal works the best. And you can examine this main rule that energy flows from high to low. So if you have a high energy place, energy is going to go to where it's low. And this kind of challenges some of our conceptions of what's going on there. So if you draw our big jar here, and you could use like a big metal bowl, you'd probably get a really similar result, or a big glass bowl. But what I have here, the bottom is that ice cube. So I'm going to summarize all of the ice in the container with just one big old giant ice cube, and that's H2O solid. And that little jar that's above it, I'm going to do a darker blue. That's H2O liquid. So that's water. And you just put your little water cup inside of a big ice container and then put salt on that ice. And you can do this at home and just watch it. I did a little too much water in that small jar, so it took a really long time. Just do a smaller quantity in that little jar and you'll get great results. So we added that salt, the sodium chloride. We put in some thermometers in both so we can measure the temperature of that water that was forming at the bottom, and then we can measure the temperature of the water that was forming in our small jar. And in our small jar, when we started, it was about 18 degrees was our initial, and then it went to 0 eventually after about 40 minutes, 42 minutes, something like that. And then in the big jar, that water down at the bottom, it started out at about 0 and then went down to about -11. So really weird that we got water down to -11 degrees. We'll have to figure out what the scoop is with that and think about the process as it goes. So graphing this, that top part of the graph is going to be the water in the small jar, okay? And the bottom part that's in green, that's going to be the water that's in the big jar. And what we're going to see is both of these just steadily decrease. So the little jar temperature slowly went from 18 to 0, and the big jar, so here's our small jar, it's going from 18 to 0, so it's losing energy. And the big jar, it's slowly going from 0 down to -11. So it apparently was losing energy too, which is, as we think about it, will become somewhat strange. And we had these two big drops, and that's where I measured what was going on near where the salt was. So the salt was quite a bit colder than the water at the bottom. So I was curious in that couple minute time frame. So then we went back here and we added our salt onto the ice. And as we added the salt onto the ice, we started to see some really interesting things. So the first thing we want to do, we'll just draw all these little green dots all over the ice here, put some salt on the big ice cube. But what we start to notice immediately is that the temperature in that small beaker starts to drop, right? And we'd expect that even if it was just in ice. It didn't have to be salt and ice. We would expect it to steadily decrease. The thing that's a little bit strange is that the temperature in the large jar also decreases. So it seems like maybe one of them would start to warm if energy's flowing from one to the other, especially if energy's flowing from the small to the larger. Maybe the large one would warm up or something, but they both get colder. So then on the outside of the jar, we had this condensation that started to form. It started to get all wet on the outside. And that happens really pretty quickly. I have to go pretty quick to get the salt in there because even with just the ice, the water will start to condense on the outside. So that water is condensing on the outside of the jar. And eventually what we started to see happening, what was really cool, where I kind of scratched the jar there, is the outside of the jar freezes. It becomes like a solid icicle out there. So that condensation eventually goes from being in the water state to being in the solid state. It goes from H2O liquid to being H2O solid. So we'll jot that down. The water on the walls froze here. And I always feel like that's really fun, that we can freeze the outside of the jar. And if you have a metal bowl that you do this in, I've done it with that and got a very similar result. You just don't want an insulated container. So when we add the salt, what I notice immediately, and it's probably harder to see in the video, but immediately the ice starts to melt. All of a sudden, you add this salt and the water starts to build up in the very bottom of that beaker. So this salt, it goes onto the ice, and we'll draw this ice now starting to melt here. So we'll show this H2O solid beginning to go into the liquid phase. And what happened at the bottom is we saw that water slowly increase as time went on. So it started out just a little water in the bottom, H2O liquid. And then by the very end, there's really a fair amount of water there. That's not a very scientific amount, but it was about 1 inch high of water that was in the bottom. And yet it was at -11. So water starts to rise as time goes on. That's one of our observations that we make. And the ice continues to melt as we add more of that salt. So the salt really is the thing that is causing that ice to start to melt. And that will be part of the fun of what we'll figure out today is what's going on with making that salt and ice? Why do we throw salt on icy roads? What's going on that makes it melt? So the temperature of the water keeps dropping as more and more water is forming at the bottom, which is like you would think maybe, like normally we'll see that water freezes at 0 degrees, and here keeps going lower and lower. Okay, so right in here, I'll just make this note also. This was my really cold area, right in this area where there was the condensation. So that area with the condensation here, it got very, very chilly, and that's where that drop was in the graph. So the area that had the salt, if you watch the video, it froze first. It turned all white. And then slowly the rest of the jar started to turn white, but definitely where the salt was near the top, I kept trying to squish it down towards the bottom, but it definitely froze the quickest right up there at the top. And eventually, I didn't end up taking a lot of those measurements, but it got down to -12, -13. So where did this water come from that was magically forming on the outside? Well, there's water vapor in the air all around us all the time. And that water vapor is a little bit higher energy. It's in the gas phase, as we'll look at that in just a moment here. But because it's higher energy, when it touches these cold walls, the cold walls are lower in energy. So these water vapors, they hit the cold walls, and as they give energy to that ice, they're going to go into a lower energy state. So the next lower energy state from water vapor is going to be the liquid. So they go from that gaseous state to the liquid. So let's draw these various states of water at different temperatures when it's just normal one atmospheric pressure. And temperature, just as a reminder, it measures the average kinetic energy. So when you're at a high temperature, molecules are moving around faster, and the cooler you get, they move around less and less. So you want to see that happening in your mind. These little molecules, the colder they are, the slower they move, and the hotter they are, the faster they move. So ice down here, our lowest temperature, lowest energy state, water in the middle, and gas at the top, our highest energy state. So as the temperature goes up, you can also think there's more energy with those higher temperatures. And at 0 degrees, that's where we have water goes back and forth, which is really kind of cool in between being an ice and being a liquid at 0 degrees. And then at 100 degrees, water goes back and forth between vaporizing into a gas and condensing back into a liquid. And if we think about what happens when we add energy to ice, melting happens. And when we add energy to a liquid, then vaporization, like boiling and whatnot, that happens to the gas. So adding energy moves us to the right here. And yeah, just as a reminder, we're at STP, so standard temperature pressure essentially. So if we add energy to that ice, we melt. If we add energy to the water, we vaporize. And then if we have steam and we cool it off, or any kind of water vapor, it condenses. And if we have water and we take energy away there, then it freezes. So when energy leaves, we move towards the left. Gas becomes liquid, liquid becomes solid. So the far right, that's our high energy when we're in the gas, and then the far left is our low energy when we're in an ice. So the higher we are, the higher energy that we have. So we'll want to be thinking about that when we go back to our diagram of the jar. So this is increasing energy that we have here. The next thing I wanted to check out is just generally what's going on. When you're ice, okay, you're H2O solid here, how is water interacting with each other? So if we draw water, water is going to make this cool sort of crystal lattice, and I'm not going to do 3 dimensions. I'll just do essentially like a cross section here. But the oxygen end of a water is going to stick to the hydrogen end of a water. And the reason for that is it has to do with the electronegativity, which if you're not familiar with is a great thing to check out. But essentially what happens is oxygen pulls the electrons closer to itself, which makes the hydrogen side more positive. So the hydrogen side is sort of positive. We call that partially positive. And the oxygen side of water is partially negative because the electrons spend more time over at that oxygen side. So the oxygen side, the negative side of water, will sort of stick to the hydrogen side of a neighboring water, and they make this cool crystal structure, a crystal lattice. And the negative is attracted to that positive, and in order to break that lattice, they're sticking together. So you think about like if you have two magnets sticking together, you have to pull them apart, and that takes energy. So what happened though when we added the salt? The salt, it sort of gets in between that bond that was made. It jumps in between that oxygen and hydrogen. So it comes in and makes it hard for the crystal lattice to form. And so it's sort of pulling them apart. So now that crystal lattice doesn't form until negative 11 degrees Celsius. So the salt interrupting that crystal lattice. But then when we have water here, we'll think about what's going on with water. Water, it also has these interactions of oxygen being negative and interacting with the hydrogen end of a neighboring one. But these ones, they can be moving around. So they have kind of these transient passing bonds, but they're there. So whenever there's hydrogen bonding to oxygen there, we call that a hydrogen bond. And so the attraction between the oxygen side of the water, which is partially negative, and the hydrogen side of water, which that's the partially positive. So that's still going on, but they're moving around because there's more energy in the system, which allows them to break those bonds and move around and then reform bonds in other places. And that, again, is because there's more energy within the system. So that ice, that's the lower energy one. And then water, we've increased energy. So now they can break apart those hydrogen bonds, that oxygen-hydrogen interaction, a little bit easier. So higher energy than ice here in our water. And the ice, that had very low energy. And the colder it gets, the lower energy it has. So now let's look at the gas. The gas, it's going to have the highest energy, right? There's the most energy within the system. So the most energy is available. So the molecules are moving really fast and they can break out of these hydrogen bonds that would want to form. So these are really transitory. They'll like maybe sort of stick to each other for a moment, but really very little. So they're moving around so much with such high energy. The hydrogen bonds don't interact as a great deal, right? Just very minimal interaction here. And the hotter we make it, the less interaction the oxygen side and the hydrogen side of a neighboring one will react. So then the energy they have is absorbed and it allows them to overcome the attractive pull of that hydrogen side of the water to the oxygen side of the water. So that one, very high energy in our gas. So that would be kind of like our water vapor that's stuck to the side of our beaker. Okay, the next thing that we're going to need to think about now that we have we have our general states of water, different temperatures, and kind of what water looks like here, we're going to look at our big beaker. Let's think about what's going on in our big beaker in terms of energy here. So our big beaker, in terms of energy, the water, because it's cooling, it must be losing energy. So the only thing that it's touching is the neighboring ice. So energy is released into the ice as that water in our little beaker cools. So what is energy going into ice going to do? Well, it's going to add energy to our ice and cause that ice is internal energy to increase and move it towards the right and potentially melt it. So energy goes into melting that ice, and some of that energy will go into the water. So as the small beaker is cooling, we have the energy going into that ice and water. Now, what about the gas? The gas, it's high energy, and as it cools, it's also dumping energy. It's going from a high energy state to a lower energy state. So the lower energy state, again, is that ice and water. So the high energy gas is giving energy into the ice and water here, which is going to, again, assist in that melting process. So it gives energy to the beakers. They cool, gets lower in energy, and so it's going to condense and become that water. And then the water, as it goes into an even lower energy state, is going to give that energy and into the ice and water, and as it freezes. So all of that energy from the outside is also getting dumped into the ice and into the water. So we would think if we have all this energy, both from the small water beaker and from the outside, all this energy is being dumped into that big beaker. The assumption is something, if you're increasing in energy, is going to increase in temperature. And that's why this is such a fun little experiment. That adding this salt kind of disrupts our expectation. So all this energy is also going into the water. So if all that energy is going into the water and ice, what should the water do if it's having energy added? It should go up in temperature. But the water temperature keeps dropping, which is just so cool. I just love it. The water temperature keeps going lower, 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 down to -11. So why in the world does the water temperature keep going down to -11? And that is what brings us to this last one. We're going to look at this equilibrium between H2O solid and H2O liquid. Okay, so H2O solid is constantly going back and forth with H2O liquid. And in order for H2O solid to become a liquid, if we're keeping the pressure the same, and H2O solid's low energy, liquid's high energy, that solid has to absorb some energy. And as it absorbs some energy, it's going to melt and become that H2O liquid. The H2O liquid then can refreeze and go back into being H2O solid. So the energy here flows from high to low, and as that liquid gives energy to that solid that it's touching, like the remaining ice cubes, it's going to cool off, and so it's going to refreeze that water. And perhaps you've experienced that with like ice cubes. You put them in a cup, and then all of a sudden the ice cubes are all stuck together because they've refrozen. It's this dynamic equilibrium. But what happens is, and that normally is at 0, when we add the salt in, all of a sudden the equilibrium gets totally messed up because the solid was getting energy and melting, becoming the liquid. The liquid was giving more energy to that solid to continue to melt it, and in the process cooling, so it refreezes. But then what happens? The equilibrium shifts. It is now H2O liquid giving energy to the ice to melt the ice, and normally this would cool the water so it would refreeze. But since salt is blocking this refreeze process, remember how it's getting in the way of those hydrogen bonds? So since salt is blocking this refreeze, it gets harder and it gets harder to make that crystal lattice. So we have to dump even more energy into that solid, which cools it even more. So the ice crystal lattice won't form until the salt is at -11, because that liquid has to keep dumping energy into the H2O solid. And eventually, there's so little energy that it overcomes the obstruction of that salt. And that doesn't happen until -11. So there it is. We have the states of water, solid, liquid, and gas. And then our various, how water's interacting here, ice, water, and gas. And then our big container, what we observed and how energy's moving. And how energy is moving out of our little container into the ice, how energy was moving from the gas into the beaker, from the water, condensation into the beaker, and all of that causing the outside water to freeze, and all that energy going into the ice right there and making that water, but still that water was getting colder. Why did that water temperature not freeze? And that brings us all back to our final little diagram here, that the solid kept getting energy from the liquid because the liquid was getting blocked by the salt. So it couldn't refreeze until enough energy left the system. And that's it. Pretty rad, huh? Well, I hope you had fun, and we'll do more soon. Great job. And what I'll try to do, I don't know if I'll be able to, I'll try to put some links on the bottom so you can look at this diagram in full if you want to zoom in on some sections, and maybe do a little worksheet that goes along with it that I put together. All right. Have a great rest of the day. Flemdog Science with me, Caleb Fleming. Subscribe, like, comment, hit that bell.